On high-frequency spin pumping in antiferromagnetic insulators. Let me just first say that the work has been done in collaboration with David Letterman, who is in California, who has done the samples, and then Van Tol in the National High Magnetic Field Laboratory in Tallahassee. But I like to do a disclaimer before I start this talk. Actually, two. The first one is that all these experiments that I will talk about have been done without the use of a laser. And that is why I like to thank the organizers for inviting me here, because I'm learning actually that I could have done this with lasers. And I'm learning a lot, very, very, very nice talks. The second disclaimer is that the results that I will present, I could do this in 5 minutes. They're very few and really preliminary. And I will give you the reason for that at the very end of the talk. So if you pay attention, you realize why. This gives me the opportunity to spend some time in the introduction, because I still have to run these 30 minutes. And I will do some advertisement of my institution. Actually, I'm the Associate Dean of the College of Science of my university, and I have the obligation to tell you a little bit about my institution. So I'll start by talking about Jairo's trip. That I kind of following his steps. I am also departing from Spain, moving counterclockwise across the Atlantic. I landed in New York University for my postdoc for 3 years, and then I moved to Florida, where I am now. I see this very unlikely, the return, so I don't see myself completing the trip unless I retire and I get back to the south of Spain by boat in a small village. Don't know. But here's where I am. This is a very beautiful picture of the southeast of the United States with Florida, the Florida. Here, sometimes actually looks like this. So the University of Central Florida is in Orlando. You may not have heard about it, but it's the largest public university in the United States. We have 65,000 students. It's not much for European standards, but for America, it's really, really a large university. You may have heard actually about the Center of Photonics. It's a very well-known center of nanophotonics. It's the College of Optics and Photonics, indeed. And of course, we share land with Mickey Mouse. And this is the High Magnetic Field Laboratory in Tallahassee, where the experiments have been conducted. All right, so a little bit about my college. I had to talk about my college, sorry. We're very well known, particularly for some research areas. It's a very large college. We have 11,000 students again. It's larger than 50% of the universities in the country. We're particularly well known because of space exploration research in connection with NASA and the Kennedy Space Center that we have in Port Canaveral around the corner. We're also very well known on ocean coastal research in general, particularly with turtles. Turtles usually lay eggs all across Florida, everywhere. And perhaps for your interest, we have the fastest laser in the world. And I had to go and talk to Zheng-Gu, who is actually a joint appointment between Creole and the physics department, where I am, and start talking about whether we can employ this to study antiferromagnetic insulators. Because I believe that there's a lot of things that you could do with lasers, as you have been showing me these last 2 days. So now my group, a little bit about my group. Well, I'm in the physics department. This is my webpage. I work in 3 main areas. My main area has always been the one that I started working in Barcelona, is single molecule magnets. I don't know if you have heard about them, but we study the quantum dynamics of spin in molecular magnets. We're now very focused on understanding the interaction between spin and photons. So some of the things that we do in that arena are very similar to the things that you were presenting today, for example. But instead of a polariton and a magnon, we work with a photon and a spin, same physics. We also do molecular electronics, in particular molecular tunnel junctions, and some spintronics. Spintronics at nanoscale, 0-dimensional with molecules, magnetic molecules, 2-dimensional. And what I'm going to be talking about today is three-dimensional because it's what we're trying now to do with spintronics with antiferromagnets, in particular with antiferromagnetic insulators. This is not just me, it's a team of players in the United States and collaborators even in Europe with experimentalists and material growers and some national labs involved. This is part of a proposal that we just submitted to the Air Force Research Office to study spintronics, high-frequency spintronics with antiferromagnetic insulators. So I'm going to talk a little bit about antiferromagnets from the point of view of spintronics. You have here some explanations about, today about antiferromagnets, but I would say that very fancy, the very detailed. I'm going to go to the very basics, right? Well, why they can, what can they offer, antiferromagnets? Well, in terms of technology applications, the main thing is the ability to operate at terahertz. Terahertz is a space in the electromagnetic radiation realm that is not easy. It's not easy to generate coherent. There is no coherent, well, little or few coherent sources of terahertz radiation. It's not easy to do and to realize. And antiferromagnets actually, as I will show you, and you know already, they operate at terahertz naturally. And this is because of the same amplification that we have here today, right? It's not just the anisotropy that plays the main role in ferromagnets, driving ferromagnetic dynamics into the gigahertz, maybe 10 of gigahertz. But here we have the combination of the anisotropy, the magnetic anisotropy, with the exchange interaction between the sublattices that amplifies that dynamics, the frequency of those dynamics by at least two orders of magnitude, and driving this into the terahertz. Well, if we take this into account and we can employ this in the way that it has been done with ferromagnets, one can think about generating terahertz signals by designing nanoscale terahertz oscillators, or ultrafast switching. Ultrafast now is picoseconds, not femtoseconds, but still pretty quick in comparison to the current technologies. And this is important for non-volatile RAM memory, for example, applications. Or it has been recently suggested that antiferromagnets can be driven in a way that they could function as artificial neurons who could be employed for neuromorphic computation. Okay, some of the potential applications. The other one is that we're dealing with something that is not magnetic. I mean, it's magnetic, but it has not net magnetic moment. So you can space elements in your memory, you're building a memory, as close as you want to each other because they won't see each other, magnetically speaking. Of course, this also carries some complications because you cannot, it's not easy to read the final state of your memory unit, right? So you have to be imaginative in order to utilize some effects in order to do that, because you won't be able to read the magnetic state of your unit. And then other things is like, for example, well, now we have degenerate magnon mounts with opposite chirality, and those can encode information. And not only that, you can actually manipulate them in different fashions, right? Like you could use circular polarized light. In this case, it would be terahertz light, or electron spin currents, many different ways, right? In particular, when we're talking about insulating antiferromagnets, those are the ones that I'm interested in. First, nothing moves. There is no charge motion. So dissipation is much smaller. And if you're dealing with a magnetic system where the dissipation is extremely low, you can start thinking about quantum magnetic effects that you wouldn't see in a metallic counterpart, for example. And well, because of that and some other properties of antiferromagnets, they have been suggested to be perfect materials for dissipation or quasi-dissipation-less propagation of really high magnon signals, really high frequency magnon signals. All right, so from the physics point of view, there's also some other things that are of very high interest, at least for our team. One of them is, well, actually you can realize a coupling between two ferromagnets through a ferromagnet that is mediated by magnons. So remember, we're talking about a ferromagnet that is an insulator. So the exchange interaction between two ferromagnets, the archaic way that you would get in two ferromagnets separated by metallic spacer, this wouldn't be possible in this case. But still, you can get the two ferromagnets to see each other with this kind of magnon-mediated interaction, right? Well, it turns out that because of magnons, the fact that magnons are bosons, they behave as bosons, no fermions, this interaction behaves with distance in a kind of monotonic way, instead of this oscillatory behavior that you get in a standard exchange interaction. But when you look at the evolution with temperature, instead of a monotonic decay that you will get as you increase temperature with the other one, here you have, this is not an oscillatory behavior because it only makes one oscillation if you want, but you can actually change the sign of the interaction between two ferromagnets by changing temperature. This hasn't been demonstrated yet. We're trying to do this. And because of that, you could also realize a magnonic spin valve that would operate with differences in temperature. That is kind of analogic to the Seebeck FET. Or things a little more sophisticated like superfluidity, where you can have this super fast propagation of signals in between two metals mediated by an antiferromagnet because of you driving the antiferromagnet into some kind of magnetic texture condensate. All right, so the simplest view of an antiferromagnet, in my opinion, relates very much to the talks this morning, but I really like to look into this material, manganese difluoride, not just because it's the one that we have measured, but also because it's a very simple antiferromagnet in the sense that it has uniaxial anisotropy. And then you look at the free energy, and then you'll find, of course, the exchange interaction between the two sublattices, the effect of the magnetic field on each of them, and then the anisotropy, in this case uniaxial, for both sublattices, and the characteristic parameters of the three interactions, right? You solve the equations of motion, and you'll find that there is a resonance frequency. So you irradiate your system with a particular frequency set up by the product of the exchange energy and the anisotropy energy. You will drive the system into a coherent precession. That is the exchange amplification that you don't get in ferromagnets. In ferromagnets, that frequency is just set up by the anisotropy. And this can be actually very high. In manganese difluoride, is 262 or 61 gigahertz, I believe, at zero field. But if you replace the manganese by iron, where the angular momentum is important, then you can drive the resonance into 1.6, and then other antiferromagnets have other frequencies. So you can play with that. And then, of course, as soon as you apply a magnetic field, you will split the generate modes into two different energies, right? And at some point, you will reach the spin flip-flop transition where both sublattices will align in the direction of the magnetic field, and then things will change. This thing here would be the response of that, of this antiferromagnet to the microwave, to the magnetic field, when the magnetic field is transverse to the anisotropy axis, this one here, right? And this was measured, actually. The spectroscopy was resolved in 1996, so 22 years ago. Well, so what if we want to employ this in spintronics? Well, basically, you want to put this antiferromagnet together with a metal or something else. And then what you want is to interconvert the spin or the spin dynamics into charge or charge dynamics, right? So you want to generate the spin current, or you want to use the spin charge current and generate spin dynamics, whatever you want to do, but that is the goal. Well, there's many tools that you can employ in spintronics. Two of the most used ones are here. One is the spin Hall effect, that is basically driving some charge current through a material with high spin orbit coupling to separate the spin polarizations of the conduction electrons into the two sides and as a result, you will generate spin current in one direction. That is perpendicular to, orthogonal to the charge current and orthogonal to the effective magnetic field that you will get there, that is basically coming from the spin-orbit coupling. Well, this basically, from charge current, you generate spin current. The other technique that usually is made to work together with the first one is the spin transfer torque. So now let's imagine that we have in a spin current a certain accumulation of spin in a material, basically a spin polarized electrons moving in one direction. Then you get into a ferromagnet in where you have magnetization, and then because of that interaction, there will be a magnetic torque that is going to try to move the magnetization of the ferromagnet, in this case, into a given direction, or even induce that ferromagnet to get into a precession and induce dynamics, right? When you combine the two, you can start manipulating and controlling your spintronic device. And this has been demonstrated for ferromagnets. With these two techniques, you can get gigahertz oscillators, or you can switch magnetization in spin bulbs down to hundreds of picoseconds or something like that, right? Now, well, if you take the reciprocal effects to these two, you could do exactly the same physics, right? So the reciprocal of spin transfer torque is the dynamical spin pumping. So basically now you don't have polarized current getting into a ferromagnet exerting a torque. Now you have a ferromagnet, in this case, precessing coherently and pumping spins in every cycle, one angular momentum, into an adjacent metal and generating spin current perpendicular to the interface. If you employ the inverse spin Hall effect, reciprocal to the spin Hall effect, you can interconvert that spin current into charge current in a way that it will be always orthogonal between each other. So the charge current will be orthogonal to the spin current and the polarization direction, right? So this is the technique that I'm using, and that is what I like to do with antiferromagnets. And this actually turns out to be very similar to what you have been doing with lasers this morning, well, these last years. You can achieve the same kind of physics somehow. Well, what has been done along this direction in antiferromagnets? Not much. Spin pumping experiments have been done in employing antiferromagnets, but the dynamics have been generated in a ferromagnet. Jig, yttrium iron garnet, the antiferromagnet sandwich in between the ferromagnet and the heavy metal, and spin dynamics generated in the ferromagnet transported through the antiferromagnet into the platinum and then, interconverted into charge. The other thing that has been done is spin transfer FMR in this heterostructure. Is related, but it's not directly spin pumping. And the closest actually to that, to the realization of spin pumping in an antiferromagnet is the group of Ross and collaborators in Munich, who have tried actually the experiment that we succeed, but they didn't. So I'm going to explain that experiment in a little bit of detail because it allows me to introduce my results. But let's first go to the theory. So now we have the free energy that we were talking about before, but now we send microwaves. Well, we send actually terahertz radiation, or sub-terahertz radiation. This is a time-dependent perturbation to the Hamiltonian. And when you look at the spin pumping, that is basically the amount of spin current that will be placed out of the, or expelled out of the antiferromagnet into the adjacent metal, is going to be dependent on this factor in where you will see that there is an anisotropy enhancement of the spin pumping that you don't actually get in a ferromagnet. So first of all, with an antiferromagnet, you will have much larger spin pumping, much larger spin currents injected into the adjacent metal than with ferromagnets. And the other thing that you can see from here, and this is resolved for zero field, is that the spin pumping will actually be dependent on the polarization of the light. So you will have to hit your antiferromagnet with either circularly polarized light. Because if you do this with linear polarization, you won't get any spin pumping, right? And you can actually look here at the magnitude of the spin current that you will generate for, dynamically as a function of this parameter here. And you will place two different materials here or there. The iron difluoride has larger anisotropy, so the spin pumping is expected to be much larger than with manganese difluoride, although we still expect to see some, right? All right, so this is the contextualization of the experiments. Now I can go to the experiments, but before going to my experiments, I will describe Rose's et al. Experiments. So these guys actually tried the same experiment by placing a single crystal of manganese difluoride, this cube here that you see, in where they have deposit, they polish the surface, they deposit a strip of platinum on top of it, and they place the whole thing on top of a coplanar waveguide. And then they pass microwave radiation through the coplanar waveguide to irradiate the sample, and from this irradiation eventually generate the spin pumping that will be measured or converted into voltage because of the inverse spin Hall effect, right? They were limited to 26 gigahertz. This is the problem of working with coplanar waveguides, but in principle, this is doable. It's well designed. It's actually a very nice experiment. They did ferromagnetic resonance. They limited to this energy. So they're only able to resolve what happens around here. But still, they do this very well. They see this resonance very nicely. They can actually look at the width of the resonance for different, in different cases. I remind you that this corresponds to the spin flip-flop transition. They have looked at what happens or how this evolves with temperature, or importantly for my experiments later, how this behaves with the orientation of the magnetic field with respect to the uniaxial axis, anisotropy axis of the material. Some calculations tells you that as soon as you get a few degrees away from the easy axis, you won't be able to resolve the spin flip-flop transition. This guy here will just move up, and eventually you won't see it. And this is what they observe here, right? All right. So the problem is that when they went to look at the voltage that they were expecting from the spin pumping in the platinum, they didn't observe anything. Well, actually, yes, they did. So this is the spectroscopy that I showed you before, and this is the voltage measuring platinum. They did a peak. They did observe a peak, but it didn't reverse with the polarity by reversal of the magnetic field, as you would expect with spin pumping, right? And then they associated this to some kind of micro-rectification in their setup, and they were basically not able to complete this measurement. All right, so we have tried exactly the same thing, a slightly different approach, but exactly the same material and heterostructure. Indeed, we tried first with manganese difluoride, a thin film, molecular beam epitaxy grown on top of magnesium difluoride, a very substrate, it's a bulk. And that is because, you know, there's an incommensuration between the lattices, but they're close. And then we deposit 4 nanometers of platinum on top of it. And then we went to the high magnetic field laboratory in Tallahassee, and we used the heterodyne detection system in where they can work with several frequencies up to, I believe it's up to 800 gigahertz, but the higher they go in power, in frequency, the lower power they get available. And in the experiments that we try, we just use these 3 frequencies, but still high frequencies, very monochromatic, not like in your case. You know, they are able to select a very particular frequency, and then our sample looks like this, and it's embedded there. This is a quasi-optical setup, so the microwaves are kind of conducted through air down to where the sample is placed, and this, of course, gets inside the magnet and so on. And the first thing that we did was to try to do spectroscopy, just to look whether we are able to do this same experiment at 100, in this case is 336 gigahertz, and see whether we see a peak here, another peak here, another peak there, right? Absorption of microwaves. We didn't see anything. what we see here is something that is totally unrelated to that, but it allows us to determine where the anisotropy axis is. But this is just manganese impurities in the substrate. But we didn't see the peaks that we were expecting. The reason for that, we believe, is that it's either because this is small, really small for this particular setup, or because it's too amorphous. Because of the incommensuration, the mismatch between the lattices in where this material is grown, maybe we lose crystallinity. And if we lose crystallinity, we cannot be talking about applying the magnetic field on the AC axis because there is no AC axis. We have a polycrystal, right? We don't know yet, but that is the fact. But then we were able to observe signals, electric signals. Actually, signals that reverse with by changing or switching the polarity of the magnetic field, as you expect from spin pumping. And the main feature that we observe for all frequencies goes in the vicinity of the spin flip-flop transition. But it's too broad, right? And it looks like there is more things here. So we were not very satisfied with this. We were associating this to the fact that we don't really have a real crystal, that we have something really amorphous. We study the evolution of the peak with power, and as you expect from spin pumping and from many other things, this grows linearly with power. We try to explain this to the best of our abilities. Maybe this is a convolution of two or three very broad peaks coming from the three places that we expect this absorption to come. But we were not really satisfied. This was about half a year ago when we did this experiment. We decided not to publish and improve the setup. All right, so 4 weeks ago, we get back to Tallahassee with a different sample. So now we took a single crystal of manganese difluoride, cut it in a small piece so that it fits in the probe, and of course by selecting the AC axis in a particular direction, and then we went back to Tallahassee to do the same experiment again, but now with a single crystal, so no polycrystal. And we did actually observe the spectroscopy that we were expecting. Two nice peaks at the positions in where you expect for this frequency, right? 5 Tesla, here you are, negative 5 Tesla, of course, it should also be there. Indeed, the absorption is too high that you're not able to resolve the signal coming from the antiferromagnet, because basically what you have is a change in the dielectric constant in your cavity. In this case, there is no cavity in the setup, and then basically you see absorption because it's there, but you're not able to resolve the line width. So we'll have to come back with a narrower crystal, and we'll have to polish that. Now, interestingly, there is no other transition. You would expect one here, right? That there is no more transitions. We understand this because we misalign between the AC axis and the magnetic field. Of course, the way to go is to rotate it a little bit and repeat the experiment. I'll let you know in a moment why we didn't do that. But we only had one day for measurements. We were coming back. We only had 1 day for measurements, so we ran into measuring the inverse spin Hall effect on the platinum that it was deposited on top of the single crystal, and we saw two nice peaks. They're very noisy, but very, very high in magnitude. This is about 50 microvolts. For the power that we were using, this is actually very nice. And we see how do they reverse with the reversal of the magnetic field. Now, this is unfortunately very noisy. We know why. We only had to change the wiring. But the problem is that Michael came 3 weeks ago and passed by Tallahassee. So they had to shut down everything. And we were scheduled 3 weeks of measurement right before this conference. And I was expecting to come with the results that I couldn't. All right? So we're planning to go back to Tallahassee. Hopefully, I don't know, because now it's a big mess, because you can imagine they have scheduled visits from all around the world to come to Tallahassee to do experiments, and they had to cancel all of them for 2 or 3 weeks, and they're just trying to get back in business. So hopefully we can do these experiments, and we're actually going to go with a better sample now that we have identified some of the problems in the second experiment. But I can give you some clues, some conclusions from what we have seen so far. The first thing is in our opinion, well, as far as we know, it's the first demonstration of spin pumping in antiferromagnetic metal or non-magnetic interfaces. Not counting laser, because maybe you're doing exactly this already, okay? Those are very preliminary results. We had to work with higher frequencies. We want to go close to the resonance at zero field or close to zero field, where we will be able to distinguish different modes by using different polarization of the microwaves. We need to get a better control of the easy axis. We knew for a fact that we were about 5 degrees out of the orientation that we wanted, because the crystal was actually cut in a wrong way. And we will polish crystals in order to get thinner and thinner, so that we can also resolve the spectroscopy, and then we can associate the line widths with the electric and the spectroscopic line widths. And then, of course, we have other things that we want to do in the longer term, like exploring other antiferromagnets and do the opposite, right? So spin pumping and looking at the inverse spin Hall effect is the first thing you need to do in order to do the opposite. That is passing current through platinum and injecting spin current into your antiferromagnet to drive it into high frequency dynamics, as you do with your lasers, and then produce the terahertz oscillators. So thank you for your attention.